Hi, and thanks for joining my presentation entitled BIM, Digital Twin, and Cyber Physical Systems, Crossing and Blurring Boundaries. My name is Dean Douglas. I'm a PhD student at Northumbria University, and I'll be presenting today on behalf of myself, Dr. Graham Kelly of BIM Academy, and Professor Mohammed Kassem of Northumbria University. There's an ever-growing interest in digital twin in the built environment, and it started a great deal of heated discussion on social media around how it relates to prevalent and well-established concepts in the industry, such as BIM and cyber physical systems. We categorized these discussions into three clusters. The first being the unconvinced, those who are dismissing the digital twin concept and depicting it either as a rebrand of BIM or a marketing invention. The second cluster is the undecided, those who are calling for greater investigation of digital twin capabilities and uses within the built environment and how these differ from those enabled by BIM and cyber physical systems before we legitimize the concept. And the third being the committed, those who have firmly accepted the digital twin concept based on various propositions, with one of the main being the sensorial connections. So how is the relationship between digital twin and these other prevalent technologies and processes being portrayed in peer-reviewed literature? In this research, we firstly look at how the relationship between BIM and digital twin is being defined, and then going on to look at the cited differences and similarities between digital twin and cyber physical systems. So how did we go about this? We conducted a systematic literature review, gathering articles from three sources: Scopus, Web of Science, and Science Direct. We gathered 168 articles in the first round, discarding those that were repeated articles, not written in English, and those that predated 2012, which is widely considered to be one of the first applications of digital twin. Moving on to having 83 articles. We then vetted articles with those that had provided no definition of digital twin. We also stipulated that they must include an application, elements, supporting technologies, or adoption of digital twin. We also discarded those that only discussed digital twin as a conclusion or a further step, in addition to the topic of the paper. And we also discarded those that was felt that the references to digital twin were considered to be speculative or not grounded. So looking at digital twin and BIM. In defining the relationships, we grouped the stances taken into three categories. The first being digital twin being seen as a continuation of BIM. The second being BIM and digital twin as two distinctly separate concepts, and BIM and digital twin as two complementary concepts. The first here, digital twin as a continuation of BIM. BIM is often seen as, often considered as a potential starting platform to build upon in the development of digital twin, often looking to integrate a number of new developments in digital technologies and processes into a BIM model, including the likes of IoT, cloud computing, and artificial intelligence. There's often a view of taking an evolutionary approach to this development from BIM to digital twin. As can be seen in the figure on the screen just now, it looks to build upon each stage of the digital twin, of the BIM model, to develop a digital twin. First, integrating asset data from sensors and employing a limited amount of analysis in the first generation there, moving on to integrate IoT devices and begin to develop semi-autonomous systems. And then in the third generation, developing a fully semantic digital twin that is capable of leveraging acquired knowledge and the use of embedded AI. There's often calls as well to utilize IFC. There's argued in the literature that digital twins could be developed using IFC to enable the integration of numerous disparate data sources. This combined with the use of COBie as an aid in the formatting of data to be integrated in digital twin. However, there's a number of challenges as well to this approach. One of the first being the definition of BIM used, with it being referred to as both a technology and an information management methodology. It's also questioned whether in the development of digital twins, in the monitoring and analysis of physical assets, is there necessarily a requirement for a 3D model? It's also argued that BIM in its current state can't deliver the information requirements throughout an asset's life cycle that would enable it to perform more complex computations such as prediction and optimization. There's also questions around the static nature of BIM asset information versus the continually updating representation of it as expected of a digital twin. Also, with the use of IFC, for it to be a viable option, there would first have to be an extension, an operation and maintenance extension to the current IFC to be developed. And with regards to COBie, the use of COBie, there are limitations to this approach due to the challenges of monitoring every single asset within a system. Therefore, its application may be limited to the critical assets where data is available. Going on to look at BIM and digital twin as two distinctly different concepts. One author explored the differences between the digital twin and BIM, comparing them in 4 attributes. The focus of application is argued that BIM applications are mainly confined in the design and construction phases of the asset's life cycle to aid communication between stakeholders, reduce design errors, and monitor time and cost in construction. Whereas the digital twin can be applied to conduct what-if analysis, to enhance occupant comfort, and to transfer lessons learned from one asset into the future design of another. Because of these application focuses, it can be seen to affect the stages of life cycle that they're involved in, as well as the users that utilize them. Continuing to look at BIM and digital twin as two distinct concepts, it was also argued that BIM is an as-built model and lacks the prompt feedback loop necessary for the continually updating representation of an asset or digital asset within digital twin. However, this point can be directly challenged by there already being examples of BIM integrating real-time sensor data. It was also said that BIM and digital twin do share a number of similarities in their strive for greater metadata of assets. However, digital twin goes further to simulate and predict asset behaviors. And then finally, looking at BIM and digital twin as complementary concepts. It can be argued that BIM and digital twin can be used in tandem at any stage of an asset's life cycle. There are a number of technologies and processes and applications such as the Internet of Things, data mining, artificial intelligence, and BIM, multiple others that are utilized for the development of digital twin. The importance of integration and interoperability of BIM and other technologies will only greater enable the digital twin. And digital twin has the potential to make use of multiple BIM models from various stages of an asset's life cycle or from a variety of disciplines involved in an asset. It was also suggested that in the pre-construction phase of an asset's life cycle, due to the lack of a physical asset to twin off of, there could be no digital twin, and therefore at this stage BIM would act as a central data repository to later feed into a digital twin. Going on to look at cyber physical systems and digital twin, these are kind of grouped into 2, looking at where digital twin is a result or a component of cyber physical systems, and then also that looking at whether the 2 are 2 distinctly separate concepts. It is offered that digital twin as a technology provided by the creation of a cyber physical system that can then become a means of simulating and monitoring an asset. Going further, to begin to understand the relationships between them, CPS is remarked as being at the core of the digitalization movement, with several different technologies, including the Internet of Things, artificial intelligence, big data, and data analytics, and cloud computing, all contributing to its creation. It's through this process of combining these technologies and the collecting of big data that digital twin is said to be created. One author also sought to understand and define the relationship between cyber physical systems, digital twin, and the Internet of Things. As can be seen in the figure on the screen, arguing that CPS encompasses both the digital twin as the digital replica of an asset, and the Internet of Things as the many sensors and controls deployed in an asset that provide the bridge between the digital and the physical entities. Going on to look at digital twin and cyber physical systems as separate yet separate concepts. They are said to differ in their origins, with digital twin having stemmed from a complex engineering background, whereas cyber physical systems originates from a complex scientific computational background. However, it is said that they share a number of characteristics, both being comprised of a physical asset and a cyber/digital replica, and an emphasis on the bidirectional flow of data between them. Both make use of applications and technologies to generate greater insights and to enhance decision making. Both create a continual cyclical loop of data between the physical and digital. Their hierarchical structures are the same, suggesting a bottom-up approach for both is necessary, starting with the definition of unit-level processes and assets until such a time that an entire system or a full asset is established. However, they do differ in emphasis. Digital twin is a highly consistent model of the physical in terms of geometry and structure, but also in its capability of simulating the spatiotemporal status, its behaviors and functions, with the high fidelity of the replica enabling the digital twin to understand and predict occurrences in the physical. Whereas CPS at its core strives to add new capabilities to the physical system by utilizing the intensive interaction of computation and communication into the physical process. Cyber physical systems is thought to follow the principles of collaboration of computing, communication, and control, which results in a one-to-many correspondence and gives a greater attention to the data exchange loop between the physical and cyber systems, and thus placing the network of sensors and actuators at its core. So moving on to the discussion and conclusion. Inconsistencies in digital twin and BIM discussion were found to be significant, and to an extent identified three different understandings about the delineations. Digital twin as a continuation of BIM outlines routes to digital twin realization that are seen to be the continuation of the BIM methodology by incorporating new technological advances, whereas BIM and digital twin as two distinct concepts highlights differences in their abilities to incorporate live data, as well as differences in the professionals and the stages of the asset's lifecycle that utilize the concept. For these two delineations, there's as many kind of counterpoints as there are points. And then the third concept, the third grouping, digital twin and BIM as a complementary concepts, digital twin and BIM as complementary concepts that can be simultaneously used to develop new capabilities such as simulation and performance and lean planning and control. The potential commonalities and differences between digital twin and cyber physical systems are seen to be further apart. Digital twin is an integral part, as an integral part of a cyber physical system. Digital twins being the vital virtual representation of an asset as a result of a number of technologies being combined. Those that argue that the two are two distinct concepts do make it clear that they share a number of common characteristics, both utilizing a variety of applications and technologies to meet their intended purposes. However, the two are said to differ greatly in their development emphasis, which in turn creates a disparity in the aspects captured, modeled within the respective concepts. Understanding the relationship between digital twin and cyber physical systems could greatly alter not only the language and terminology used when discussing the components of a digital twin, but also the applications in the future. The key recommendations being made here is, if the built environment is to realize the potential benefits of digitalization, future research should strive to build consensus around the commonalities, differences, and interactions between the concepts of digital twin, BIM, and cyber physical systems. if this challenge is not addressed, the risk of compromising the reusability of knowledge that is available in the industry and academic literature. This will also partly contribute to the slowing down the digitalization of the construction sector at a time when the sector is facing new challenges and has been asked to become more efficient than ever before. Thank you for taking the time, and if you have any questions.